All right, welcome to the classroom. Today we're going to have a look at the first lesson of chapter 4. We're going to talk about work done by a constant force and kinetic energy and work energy theorem. Okay, first of all, let's have a look at the first section in this chapter, work done by a constant force. Studying can feel like a lot of work. Imagine studying several hours for a difficult test or spending all afternoon writing a report for class. Well, this is a significant amount of hard work. In the scientific sense of the word, you have done no work at all. In physics, work is the energy that a force gives to an object when the force moves the object. When you read your notes, you do not work. You do no work because you do not exert a force on an object to move it. Your everyday life, however, is filled with examples of work in the scientific sense. You do work on a backpack when you lift it to your shoulders. You do work on the classroom door when you push it open or pull it closed. You do work on a basketball by bouncing or throwing it. In these cases, a force does work on an object to move it. You may notice that you do more work lifting a backpack filled with heavy books than lifting an empty one, and more work lifting a backpack from the floor than from a desk, because the distance from the floor to your shoulder is greater than the distance from a desk to your shoulder. The scientific definition of work is consistent with this experience. Okay, so now let's have a look at the concept of work. Work depends on the magnitude of the force applied to an object and distance the object moves. In fact, work depends only on the object's displacement in the direction of the applied force, and not displacement perpendicular to the force. In other words, the work depends only on the component of force in the direction of motion and not the force perpendicular to the motion. Suppose, for example, you are shoveling snow. You might push on the snow at angle theta to the ground, but the snow moves horizontally, which is shown here in figure 1. The component force directed into the ground does not help move the snow across the ground. Only the component force along the ground moves the snow. In any situation, only the force in the direction of an object's displacement does work on the object. The equation for calculating the work W that a constant force F does to cause the displacement delta D of an object is given by this formula here. W equals F delta D cosine theta, where F is the magnitude of the force, delta D is the magnitude of the object's displacement, and theta is the angle between the force and displacement. The component of the force in the direction of the motion is F times cosine theta, which is shown here in figure 2. So the work done by a force depends on two vectors, the applied force and the resulting displacement. The work done on an object is proportional to both force, F, and displacement, delta D. However, the amount of work done is a scalar quantity, not a vector. So you need to be careful with this. The work is a scalar, not a vector. The SI units of work are Newton meters, or kilograms times meters squared per second squared. This unit is called a joule, which is abbreviated as J. So now let's have a look at a tutorial in which we'll explore how to use the work equation to determine the work done in different situations. Okay, so now let's consider tutorial 1, calculating work done. Okay, let's consider the sample problem 1, calculating the work done when the force is parallel to the displacement. The displacement of an object is often in the same direction as applied force. In this case, the equation for calculating the work done by the force is simplified. Suppose a hockey player slides a puck along the ice with a constant force of 85 newtons in the forward direction, which is shown here in figure 3. The puck moves a horizontal distance of 0.20 meters while in contact with a hockey stick. Can you calculate the amount of work done on the puck by the stick? Okay, I'll give you 5 minutes to consider this simple problem here. All right, have you finished? So this question is pretty straightforward, right? So the given information is force is a 5 newtons. The displacement, the force exerted on the punk is 0.20 meters. So we need to find the work done by the stick. We can use the equation for work, W equals F delta D cosine theta, to find the work done by the stick. F and delta D are in the same direction, so we know the angle between them is 0. So cosine 0 is 1, right? So W equals F delta D times cosine theta, which is 85 newtons times 0.20 meters, which is 17 joules. So we can make the final statement. The hockey stick does 17 joules of work on the punk. Also note that the stick only does work on the punk while the stick is in contact with the punk, applying force. Okay, do you have any questions? Okay, if no questions, let's consider sample problem 2. Calculating work done by when the force is at an angle to a displacement. The applied force and displacement can be at an angle to each other. For example, a student pushes a lawnmower forward with a constant force of 48 newtons for displacement of 7.5 meters, which is shown here in figure 4. The angle between the force and displacement of the lawnmower is 32 degrees. Calculate how much work is done on the lawnmower by the student. Okay, again, I'll give you 5 minutes to consider this question by yourself, and then we'll have a look at the solution together. All right, let's have a look at the solution together. It should finish now. Okay, again, similar to previous question, the given information is, you know, the force, magnitude of force is 48 newtons, and displacement is 7.5 meters, and the angle between the force and displacement is 32 degrees. So the work done on the lawnmower by the student depends only on the component of the force in the direction of the mower's direction, displacement. Use the equation for work. W equals F delta D cosine theta. F and delta D are at an angle of 32 degrees to each other. So put all the values in. We know the work done by the force is 3.1 times 10 raised to the power of 2 joules. So the student does 3.1 times 10 raised to the power of 2 joules of work on the lawnmower. Okay, do you have any questions? All right, if no questions, let's consider another problem. Sample problem 3. Suppose you carry books with a weight of 22 newtons with a displacement of 3.8 meters across the room, which is shown here in figure 5. Can you determine the work done on the books? Okay, I'll give you 2 minutes to have a quick look at this question. Okay, have you finished? What's the result here? Okay, so note here the work done by the force is given by F delta D cosine theta, right? So apparently in this case, the angle between the force and displacement is 90 degrees. So cosine 90 degrees equals 0. That means no work done on the books. Okay, any questions? Okay, so the work done could be positive or negative. This can be found by using the formula to calculate the work, right? Because the work done is given by F delta D cosine theta. So apparently when theta is between 90 degrees and 80 degrees, cosine theta will be a negative number, right? So the work done could be either positive or it could be negative as well. For example, in sample problem 1, the force of the hockey stick on the punk resulted in positive work that caused the punk speed to increase. So what if the punk slides to rest? The displacement of the punk and the force on the punk by friction are in opposite directions. When an object moves in a direction opposite to applied force, the applied force If the force does negative work will cause a loss of kinetic energy. Forces that cause negative work are exerted at an angle between 90 degrees and 180 degrees, opposite to the object's direction. So in previous chapter, we know that friction is the force resisting the motion of objects moving against each other, right? So next, let's have a look at tutorial 2, in which we have an opportunity to calculate the negative work that occurs when a force such as friction and displacement are in opposite directions. Okay, now let's consider this sample problem here. Suppose a car is moving along a straight road when the driver suddenly applies the brakes. The force of friction between the ground and the car tires is opposite to the car's direction of motion and decreases the car's speed. Calculate the work done by a constant frictional force of 1.4 kilonewtons over a distance of 1.2 times 10 raised to the power of 2 meters. Okay, I'll give you 3 minutes to consider this problem quickly, and then we'll have a look at the solution together. Okay, you should finish now. So the work done by the friction force is given by W equals F delta D cosine theta, right? So here we know cosine theta is actually cosine 180 degrees. So put all the values in. We have the work done is negative 1.70 times 10 raised to the power of 5 joules. So the negative sign here indicates that the force is opposing the motion. Okay, any questions? All right, if no questions, let's consider another problem. An ice skater slides to a stop by pushing her place against ice, which is shown here in figure 6. The ice exerts a constant force of 95 newtons on the skater, and skater stops in 1.2 meters. The angle between the force and the skater's direction of motion is 140 degrees. Can you calculate the work done on the skater by the ice? Okay, I'll give you 5 minutes to consider this problem by yourself, and then we'll have a look at the solution together. All right, have you finished? Okay, let's have a look at the solution together. So in this question, still we're using the formula of W equals F times delta D times cosine theta to find the work done on the skater by the ice. But note here, the force exerted on the skater and displacement, they have an angle between 90 degrees and 180 degrees, right? So you will expect you will get a negative number here. So put all the values in, we have W equals F delta D cosine theta, which is 95 newtons times 1.2 meters times cosine 140 degrees. And that's approximately negative 87 Newton meters or negative 87 joules. So the ice does negative 87 joules of work on the skater. Okay, do you have any questions? Okay, so if you don't have any questions, let's consider a special case when the situation involves an applied force in which zero work is done. So when the direction of an object's displacement is exactly 90 degrees to the applied force, the force does no work on the object. Look back on sample problem 3 in tutorial 1, which is here. As a student walks across the room, he pushes up on the books, but the books move to the right. The angle between the force and displacement is 90 degrees, right? So according to the formula of the work done by the force, W equals F delta D cosine theta, we know cosine theta is actually cosine 90 degrees, which is 0. Therefore, the student does no work on the books. The work also equals 0 when the force on the object is 0. Consider a probe traveling in space far from any gravitational forces. The probe's motion is due to inertia, but the force on it is 0. As a result, 0 work is done on the probe. The third variable in the work equation is the displacement of an object. Have you ever tried to twist the lid off a jar, but the lid was stuck? Regardless of how much force you exert on the lid, you do 0 work unless the lid moves. The work on the object is 0 when any of the force, displacement, or the cosine of the angle between the force and the displacement is 0. So next, let's have a look at another tutorial 3, in which we'll examine another example of a force that does 0 work. Okay, so let's consider this sample problem here. A student attaches one end of a spring to a rubber stopper. She then holds the other end of the spring and twirls the rubber stopper in a horizontal circle around her head. The string exerts a tension force on the stopper directed towards the center of the circle, which is shown here in figure 7. Can you determine the work done on the stopper by the string during a revolution? Okay, I'll give you 5 minutes to think about this problem by yourself, and then we'll have a look at the analysis together. All right, let's discuss this problem together. So here we know the angle between the force and the displacement is 90 degrees, right? And we want to find the work done by the force. The tension force Ft causes the stopper's centripetal acceleration. At each moment, stopper's instantaneous velocity is at an angle of 90 degrees to the tension force. During a very short time interval, the very small displacement of the stopper is also at angle of 90 degrees to the tension force. You can break one loop around into a series of many small displacements, each occurring during a very short time interval. During each time interval, the tension and displacement are perpendicular. The total work done during one loop around will equal the sum work done during each very small displacement. For each small displacement, you can use work equation W equals F delta D cosine theta, with theta equals 90 degrees. Therefore, W is 0 joules. So summing the work done during all the small displacements of the loop gives us a total of W equals 0 joules during each revolution. The tension force exerted by the spring does 0 work on the stopper during the revolution. Okay, do you have any questions? So in this tutorial, the work does not depend on the magnitude of the tension force or the total distance the stopper moves. We treated the stopper's orbit as a series of tiny displacements perpendicular to the tension force. For each tiny displacement, the tension force does 0 work on the stopper. We conclude that the work done by the centripetal force acting on an object in circular motion is 0. Okay, so next let's have a look at the work done by multiple forces. Almost all real-world examples of work involve friction plus other forces. So now let's consider tutorial 4, in which we explore how the presence of multiple forces affects the work done on on an object. So now let's consider this question here. The hiker exerts a constant force of 135 newtons on a sled at a 48 degrees angle to the sled displacement. At the same time, a constant 67.0 newtons frictional force on the sled from the snow opposes the motion. The sled also experiences a force from gravity and normal force from the snow. But these forces do not contribute to the work because they are perpendicular to the displacement, right? So can you calculate the work done by the hiker, the work done by friction, and the total work done on the sled when the hiker pulls the sled 345 meters over the snow? Okay, I'll give you 5 minutes here to consider this problem by yourself, and then we'll have a look at the solution together. You can start now. All right, let's have a look at the solution together. So first of all, we can use letters to denote the given information. The magnitude of the force applied by the hiker is 135 newtons. Magnitude of frictional force is 76.0 newtons. Oh, sorry, 67.0 newtons. And the displacement, magnitude of this displacement, delta T equals 345 meters. And the angle between the Fn and the displacement is 48 degrees. And theta F is 180 degrees, which is the angle between the frictional force and the displacement. And we want to find the work done by the hiker, WH, by the frictional force, WF, and by the tension, WT. Oh, sorry, the total work is denoted by WT, not the tension. Okay, so we can use the formula for the work to find these works. First of all, WH equals FH delta D cosine theta H. Put all the values in, we have WH equals 3.116 times 10 raised to the power 4 joules. And WF equals FF delta D cosine theta F, which is approximately negative 2.312 times 10 raised to the power 4 joules. And WT, the total work done, is actually sum of the WH and WF, right? Which is given by 3.116 times 10 raised to the power 4 minus 2.312 times 10 raised to the power 4. So note here, the work is a scalar quantity, so we can sum of these two numbers directly, right? So the final answer, total work done is 8.04 times 10 raised to the power of 3 joules. The hiker does 3.12 times 10 raised to the power 4 joules of work on the sled, and friction does negative 2.31 times 10 raised to the power 4 joules of work on the sled. And the total work done on the sled is 8.04 times 10 raised to the power 3 joules. Okay, any questions? So this tutorial showed us that a frictional force is present in many parts of the hiker and sled problem. Friction acts, for example, between the hiker's hands and the rope, between the rope and the sled, and between the hiker's boots and the snow. A frictional force acts and does work on any surfaces that slide past each other. In each case, the frictional force transfers energy to surfaces, increasing their kinetic energy. The energy does not disappear. The increase in temperature occurs because of the motion of items at the surfaces. All substances are composed of particles in constant motion. When friction hits two surfaces, the vibrations of particles become larger, and the particles move more quickly. The faster moving particles have more energy, and energy stored in the chemical bonds increases. In a summary, when analyzing the total work done on an object, all forces that are present, including friction, must be considered. The net effect of these forces can result in either positive, negative, or zero total work done on the object. Okay, now let's have a look. Now let's take 10 minutes break. And after that, we'll have a look at the second part of this lesson, in which we'll talk about the kinetic energy and work energy theorem. Okay, you can take 10 minutes break now. All right, welcome back. So now let's have a look at the second part of this lesson. We're going to have a look at kinetic energy and the work energy theorem. So imagine the energy that a jet, like the one in figure 1, needs to climb into the air. The jet has a mass of hundreds of thousands of kilograms. Yet during takeoff, it seems to rise easily above the ground. How can the jet have so much energy? You read in the previous section that the work of a force does on an object is proportional to the distance objects move. The work is also proportional to the component of the force in the direction of the object's displacement. The jet engines cause the force that pushes the engine forward. As it moves along the runway, air rushing past the wings exerts an upward force on the wings. The engines help maintain this effect. The forces of the engines and the air do work on the jet as it takes off. So in this part of this lesson, we'll learn about the relationship between the work done on the object and the energy transferred to the object. The jet engines and the air are the sources of energy that the jet uses to fly. Okay, first let's introduce the concept of kinetic energy. Kinetic energy, which is usually denoted by EK, is the energy an object has due to its motion. An object's kinetic energy is directly related to its mass and the square of its speed, according to the following relationship. EK equals 1/2 times m times v squared, where m is the mass of the object and v is its speed. So now consider how this relationship affects the kinetic energy of the jet in figure 1, which is shown here. The jet's kinetic energy increases during takeoff because its speed increases. If the speed doubles, for example, the kinetic energy increases by a factor 4. The jet has a tremendous amount of kinetic energy because its mass is so great. Also notice that kinetic energy is a scalar quantity as well. The equation above defines the magnitude of the kinetic energy, but kinetic energy does not have direction associated with it. The mass and speed of the airplane, and not its direction, determine its kinetic energy. We can use dimensional analysis of the above equation to identify the units of kinetic energy, expressing the mass in kilograms, kg, and the speed in meters per second, m per s, shows that units of kinetic energy are also joules, which is denoted by J. Notice that units of kinetic energy are the same as units of work. We will explore this important result further after the next tutorial. So first, let's have a look at a sample problem in tutorial 1. A car has a mass of 1.5 times 10 raised to the power of 3 kilograms and is traveling at a speed of 85.0 kilometers per hour. Can you calculate the car's kinetic energy? Okay, this problem is pretty straightforward. I'll give you 5 minutes to find this kinetic energy. Okay, you should finish now. So if we know the mass of the object and the speed of the object, we can directly use the formula to calculate its kinetic energy, right? EK equals 1/2 times m times v squared. So put all the values in. Be careful with the unit here. We want to convert the unit to SI unit for each quantity here. So 85 kilometers per hour is 23.6 meters per second. Okay, so put all these values in. The kinetic energy of the car is approximately 4.18 times 10 raised to the power of 5 joules. Okay, any questions? Okay, if you don't have any questions, let's consider another sample problem. We can also use the kinetic energy to determine the speed of an object. When fleeing a predator, a 1.4 kilogram rabbit has a kinetic energy of 96 joules. Can you calculate the speed of the rabbit? Okay, I'll give you 3 minutes to consider this problem by yourself, and then we'll have a look at the solution. All right, let's have a look at this question together. Okay, we can rearrange the kinetic energy equation from EK equals 1/2 of mv squared to isolate the unknown variable v. So v equals a square root of 2ek over m, right? And then put all the values in. We have the speed of the rabbit is approximately 12 meters per second. Okay, do you have any questions? Okay, if no questions, let's have a look at another concept, which is called the kinetic energy and work energy theorem. Newton's second law of motion tells us that when an object is subject to a net external force, it accelerates in the same direction as a force, right? This motion results in work being done on an object. When the object's speed changes from this acceleration, then its kinetic energy also changes, which is illustrated in figure 2. We have seen that for the simplest case of one-dimensional motion, with the force directed parallel to the displacement, the work done by a force on an object is equal to the magnitude of the force multiplied by the object's displacement. That is W equals F delta D, right? Using Newton's second law, Ft equals ma for this one-dimensional case. This equation then becomes W equals Ft delta D. Then W equals ma delta D, right? Assumes that the force is constant, so that acceleration is also constant. Recall the following kinematics equations for motion with constant acceleration. We have v squared equals v initial square plus 2a delta d, right? Notice that the subscript I indicates the initial velocity and position, and the subscript F indicates the final velocity. The displacement is just delta D over dF minus dI. So v squared equals vi squared plus 2a times dF minus di. Or we can also rearrange that to a times difference between dF and di, which is actually delta t, right? Equals vf squared minus vi squared over 2. To calculate the work done on object as it moves from initial position di to the final position df, we can combine the previous equations. Then w equals ma times df minus di, which is m times vf squared minus vi squared over 2. And simplify this gives us w equals 1/2 of m times vf squared minus 1 over 2 times m times vi squared. The equation shows that doing work on an object changes its kinetic energy. The following shows this relationship explicitly. So 1 over 2 mf squared is actually the kinetic energy in the final state, right? And 1/2 of m times vi squared is the kinetic energy in the initial state. So that's the difference between EKF and EKI. In other words, W equals delta EK. So this equation is called the work energy theorem, which means the total work done on an object by an external force equals the change in its kinetic energy. This relation tells us how work, force, and displacement connect to the kinetic energy of an object. Notice that This theorem is also consistent with the result discovered earlier, that work and kinetic energy are both measured in the same units, joules. Okay, now let's consider a tutorial here, applying the work energy theorem. We can use the work energy theorem to solve problems involving the kinetic energy transferred when a force does work on an object. Okay, so now let's consider sample problem 1 in tutorial 2. A blue whale with a mass of 1.5 times 10 raised to the power 5 kilograms is swimming with a speed of 6.1 meters per second. A nearby boat startles the whale, and the whale increases speed to 12.8 meters per second. Calculate the work done on the whale by the water. Okay, I'll give you 5 minutes to consider this problem, and then we'll have a look at the solution together. All right, let's have a look at the solution together. So as the whale swims, it exerts a backward force on the water. By Newton's third law, the water exerts the equal and opposite forward force on the whale, causing it to accelerate to gain kinetic energy. We can use a work energy theorem W equals delta EK to calculate the positive work done by the water on the whale. So first, we can determine the initial and final kinetic energies. Initial kinetic energy EKI equals 1/2 times m times vi squared. And this is approximately 2.979 times 10 raised to the power of 6 joules. And the final kinetic energy is EKF equals 1/2 times m times Vf squared. And this is approximately 1.23 times 10 raised to the power of 7 joules. Then we can apply the work energy theorem, W equals delta EK, which is the difference between the final kinetic energy and initial kinetic energy. Put all the values in, then we know the work done by the water is 9.5 times 10 raised to the power of 6 joules. Okay, do you have any questions? Right, if you don't have any question, let's consider another sample problem. A shuffleboard player wants to slide a 430-gram disc a distance of precisely 12 meters. If the coefficient of kinetic friction between the disc and the plane surface is 0.62, calculate the initial speed at which the player must release the disc. Okay, again, I'll give you 5 minutes to consider this problem by yourself. All right, now let's consider the solutions here. So the work due to friction is Ff equals mu k Fn, right? Where Fn is normal force. Calculate force due to friction, then the work done by friction. The work done by friction is W equals Ff delta D cosine theta. The work energy theorem is W equals delta Ek, and Ek is 1/2 of mv squared. So first, the force due to friction is Ff equals mu k Fn, which is 2.61 newtons. The friction opposes motion of the disk, so theta is 180 degrees and cosine theta is -1. Therefore, the work done by friction is given by W equals F delta D cosine theta, which is -31.3 joules. The work energy theorem tells us that the change in kinetic energy will equal the work done, or -31.3 joules. The final velocity is 0, so the final kinetic energy is also 0, right? And the initial kinetic energy is the negative of the work done, which is Ek equals Ef minus Ei. And this gives us Ek equals 31.3 joules. We can solve for the initial speed. Ek equals 1/2 mv squared. And put all the values in, we have v equals a square root of 2 Ek over m, which is approximately 12 meters per second. So the initial speed of the disk must be 12 meters per second. Okay, do you have any questions? All right, if you don't have any questions, let's consider another sample problem. Here, a police car of mass 2.4 times 10⁻³ kilograms is traveling on the highway when the officers receive an emergency call. Increase the speed of the car to 33 meters per second. The increase in speed results in 3.1 times 10⁵ joules of work done on the car. Can you determine the initial speed of the police car in kilometers per hour? Okay, I'll give you 5 minutes to consider this question by yourself, and then after that, we'll have a look at the solution together. So be careful with the unit here. All right, now let's consider the solutions to this question. So we can rearrange the work energy equation to solve for the initial speed of the car, right? First, we can calculate final kinetic energy of the car, then subtract the work done to determine the initial kinetic energy. Okay, so first determine the final and initial kinetic energies. Final kinetic energy is 1/2 times mvf squared, which is about 1.31 times 10 raised to the power of 6 newtons. Oh, sorry, this unit here is not Newton, but should be joules. Sorry for the typo here. And W equals delta EK, which is difference between EKF and EKI, right? On the other hand, EKI is EKF minus W, which is 1.31 times 10 raised to the power of 6 minus 3.1 times 10 raised to the power of 5 joules. Then EKI is 1 times 10 raised to the power of 6 joules. Then we can solve for our VI. EKI equals 1/2 of m times VI squared. And from this equation, we can find VI equals square root of 2 EKI over m. And then put all the values in, we have VI equals 28.9 meters per second. So the initial speed is 29 meters per second. But this question asks us to give the speed in kilometers per hour. So we have to convert the unit from meters per second to kilometers per hour. 28.9 meters per second equals 1.10 raised to the power of 2 kilometers per hour. So the initial speed of the police car was 1.0 times 10 raised to the power of 2 kilometers per hour. Okay, so please have a look at the solution. Any questions, just let me know, okay? Okay, so we have learned the work energy theorem. Another issue I need to mention is that we can use the work energy theorem to solve several types of physics problems. However, we cannot control all of the variables in the real world as easily as we can in a physics experiment. The work energy theorem is only true if no energy losses occur. In many real-world situations, energy will seem to disappear in the form of light, sound, heat, or changes in the shape of an object. For instance, in a car collision, energy goes into the sounds of the crash and the bending of materials in the car. The work done on a given car does not equal the change in kinetic energy of that car. This discussion assumes that the applied force is constant. The derivation of the work energy theorem for a varying force requires calculus, but the result is the same. The work energy theorem holds true, even when the applied force is not constant. Okay, so that concludes our lesson for C4L1. Remember to complete the homework on Google Classroom and submit them before the deadline, okay? I'll see you next time.